The width of our rectangle is decreasing at a rate of 2 inches per minute, and the length is increasing at a rate of 1 inch per minute. At what rate is the length of the diagonal changing when the width is 5 inches and the diagonal is 13? So I'm going to sketch my rectangle first. So we've got our length and our width. If you have them flipped around, that's fine. But then I'm also going to draw in the diagonal. So that's what's going to create our right triangle. Okay. Now, nothing gets a number in this picture, okay, because everything is changing. Okay, the width is decreasing, so this side is getting shorter. The length is increasing, so this side is getting longer, which means our diagonal is changing as well. Okay, so if we look at the two numbers they give us, they both come after the word when. So that's how I know don't put them in the picture. So my equation here is going to be length squared plus width squared equals the diagonal squared. Then I'll take my derivative. That'll be 2L and then dl dt. So every derivative gets a dt with it because we're now taking the derivative with respect to time. Then 2W dw dt equals 2d and then a dd dt. Okay. Now if you want to, since everything has a 2, you can go through and divide by 2. If you wait till the end, that's fine. I'm just going to wait till the end. Okay, so then we've got, for our regular variables, that's just length, width, and diagonal. Okay, so these are just the regular lengths. Okay. Then we've got dl dt, I'm just going to write dl, dw dt, and dd dt. So these are our rates. So I'm going to go back to the problem. It says the width of the rectangle is decreasing at a rate of 2 inches per minute. So the fact that it's decreasing tells me it's negative, and it's the rate for the width. So that would be my dw. So that'll be negative 2 inches per minute. The length is increasing, so that means it's positive, at a rate of 1 inch per minute. So that's the rate for the length. And then at what rate is the length of the diagonal changing? So they're wanting the rate for the diagonal, so that's the dd dt. When the width is 5, so that's going to make this 5, and the diagonal is 13. Okay, so this is what they're asking for. So I'm still missing W. So I'm going to go back to the equation and plug in my width and my diagonal. So that'll be length squared plus width squared. So 5 squared is 25 equals the diagonal squared. So 13 squared, 169. Subtract 25 and square root it, and this one will end up being a perfect square. So I'm going to go ahead and write that as 12 inches. Okay. Then I can take all of this, plug it into the derivative, and solve for dd dt. So I'm going to have 2 times 12 times 1 plus 2 times 5 times negative 2. That'll be 2 times 13, and I'm missing my dd dt. This is what we're trying to solve for. So I'm going to figure out this side first. So I'll do 2 times 12 plus 1, that's 24, plus 2 times 5 times negative 2, that's negative 20. So that'll be 4 equals 26 times dd dt. Divide by 26. And then 4 divided by 26 will give me the rate at which the diagonal is changing, and that is 0.154, and my rates are in inches per minute. So since this rate is positive, it means the diagonal is increasing in length at that point.